Okay, so one of the first things I said was this chapter is definite integrals. And I showed you what the topic tile means, right? When we're taking definite integrals, the two ends are defined. So definite or defined integrals, you have a start and end point, and you're finding the area under the graph between your two endpoints. That is literally the most basic summary I can give you. Now, 5.1 is estimating with finite sums. So let's think of distance traveled. Throw back to physics. Consider the following problem. A train moves along a track at a steady rate of 75 miles per hour. So it's not changing, right? It's just going, chugging along, constant velocity. We're not accelerating, right? We're not speeding up, slowing down, no brakes, just going 75 miles per hour. From 7 a.m. to 9 a.m. Pretty cool. What is the total distance traveled by the train? Okay, so in physics, or I think in middle school, they even did this by applying the formula D equals R times T, right? Distance is just rate times time. We can find, okay, D, distance is, distance. So the rate is 75 miles per hour, right? This is our rate. If we multiply by our time, it's 2 hours, right? The distance, it's 2 hours from 7 a.m. to 9 a.m. What happens to my hour units? Are we okay? Okay. Say your chin inches?
I feel jittery.
Oh, too much coffee or something. Or adrenaline, yeah.
Woo! I need to start the day.
That's me.
Bro, what happened to the guys' game yesterday?
Oh, you guys done?
They lost, unfortunately. Like 30 points. It was a close, okay. 2 times 75.
5.5 minutes of the JV game was fire.
Yeah. You're telling me I was having anxiety because I had to run the clock.
Because I've done the same, like I've done the scoreboard at my camp when it's a close game, and I
It was terrifying.
like yelled at my friends. I was like, guys.
All right, so let's keep going. So we know if it's going at a steady rate, it's going 150 miles per hour. Let's make a connection between this formula and the graph of the velocity function. Okay, let's focus. So we have velocity as the y value, right? This is velocity. Oops. What is our velocity? 75 miles per hour. Okay. And let's see. Are we changing our velocity at all?
No.
No, so it's constant velocity. So it's just going to be a straight line across. Right? Just a straight line across at y equals 75. And this bottom one is our time. So if I'm going from 7 a.m. to 9 a.m., this is a difference. The length is 2 hours.
Well, wouldn't the graph have the 7 a.m. on the 0?
No, not necessarily. Maybe the train, like, we only care about between 7 a.m. and 9 a.m. But what about maybe it was going that right beforehand?
All right.
Ty. Make you walk up here. Okay, so we're trying to make a connection between the formula D equals R times T and this graph. So notice I listed out my starting 7 a.m., my end 9 a.m. I have my rate 75 miles per hour. So wait, if I take if I want to find the area of this rectangle in purple I just drew, the area of the rectangle, think what it would be. Don't say it out loud. The area of a rectangle. Okay, what is the simplest formula, right? Area is base times height. Okay, area is base times height. So here, what is my base? 2 hours. What is my height? 75 miles per hour. Oh my gosh, guess what? We get 150 miles. So it's connecting to our equation, D equals RT.
But isn't it just looking for that?
I can't answer 2 questions at once, so I'll hit Abby's and then yours.
Isn't it just looking at the 7 a.m. to 9 a.m. slot? So how do you use the whole 75?
So the base is this 2 hours. The height right here, this is at 75.
Oh.
Yeah.
Okay.
Because I only want the area of this guy right there.
Yeah.
Okay. So notice the distance traveled by the train is exactly the area of a rectangle whose base is the time interval from 7 to 9 and whose height at each point of the value is a constant 75. All right, we feel good so far, right? Yeah, so we got to have a positive mindset when we approach this. Even if your friends in AP Calc, AB said it's hard, like we're fine, okay? You do you. You're only competing against yourself. Don't listen to those hooligans, okay? I just need you to not stop yourself before you even give it a chance. Okay, that's all I want. I just want you to try it. Now, guess what? Maybe there's I don't know, a deer running along, or maybe the train engineer sees a shooting star, so he like slams on the brakes or something, okay? What if the train has a velocity that varies as a function of time? Ooh.
We can do a triangle for this one. I'm feeling a triangle.
Well, let's see. Let me draw a function. So maybe something like this, right? And let's go from, once again, 7 a.m. to 9 a.m. Where's my purple? Ooh, right? This is not a nice triangle, right? We can't find the area with a nice triangle. But what I'm trying to do, I know the area is going to be, let's see, this right here is my time. This, oops, I should probably pick a different color when I'm doing this. Okay, so this portion is my time. The vertical is just representing my velocity. So would the area of this irregular region still give the total distance traveled? Yeah, the area will still tell you. Because if I take this little chunk right here, it's roughly, if I take small little slices and see the distance, okay, how far did it travel in these 5 seconds? How about now the 5 seconds? And I add up all the intervals of 5 seconds until I reach a total time of 2 hours. I know exactly how much it's traveled at all those little intervals. Let me, right, so instead of taking, the whole time of 2 hours times the height, 'cause it's not a perfect rectangle, maybe if I could break this up into small parts, right, like maybe make this a small little slice right here, so it'd roughly be the same height. I could have lots and lots of small rectangles, and I just add them all up, and then I could get a distance.
What if the line?
Welcome. That's it. That's an integral. That's all you're doing. You're just breaking your weird function because it's not flat on top. You're just breaking it up into very, very skinny rectangles, very, very skinny rectangles, and you're just going to be adding up all the rectangles because that's the total distance. That's exactly the first thing I tried showing you on the topic page. Like that's the idea. Okay, and the first, what is it? The first 2 lessons, it's just mostly, okay, cool, let's split it up into rectangles. Now let's split it up into trapezoids. That's the first 2 lessons. Okay. Sorry, someone had a question?
Oh, yeah. So let's say the line, like that squiggly you have there, what if it was like really drastic? That's not the same. You know.
So you mean if my graph looked like something? If it looks something like this, like that?
Yeah, like at
okay.
that point it's gonna be.
So I could take like this chunk, and this starts getting the trapezoid rule. Like what if instead of rectangles we had trapezoids? Or it gets into, we want to draw a rectangle. Do I have it so the right point is on our graph? Do I have it so that the left point touches our graph? Or do I have it so the midpoint of my rectangle touches? There you go. That's the whole lesson. Literally, this is it. The left-hand endpoint, the right-hand endpoint, the midpoint. Yeah, and then we just practice. So, cool. It's good that you are seeing the progression. So, would this area still give the total distance traveled over the time interval? Yes. Newton and Leibniz thought it would. These are the 2 famous people that invented calculus independent of each other. So imagine the time interval being partitioned into many tiny subintervals, each one so small so the velocity would essentially be constant. Right? So very, very minuscule. We're talking about 2 hours of a time. Like what if I have it split into 5-minute increments, or maybe a minute, or maybe every single second, right? You're not speeding up that much in 1 second. So we could roughly find out how much distance it travels this second. Okay, now this second, we just add up all the distances. Geometrically, this is equivalent to slicing the irregular region into narrow strips, each of which would be nearly indistinguishable from a narrow rectangle. Okay, I gotta draw this again. Okay, blah, blah, blah. Here's my y value, and I'm going from 7 a.m. to 9. So here's a slice, 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 slice. I'm slicing into really, 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 really thin parts. Slice, 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 slice. Okay, I'm not really good at drawing straight lines clearly, but I'm slicing them into very, very thin rectangles. So if I want to pick like this guy right here, right, the area of this is going to be whatever your like small x is, right? It's a small interval of time times your velocity. Well, here your velocity, your height, is just your y value. Y value is height, and thanks to 4.6 related rates, we're like, oh yeah, we can, or I think 4.4. We're like, oh yeah, the height here is literally the y value, and our y value is a function, because our y value is going to be changing. They argued, right, Newton and Leibniz argued the total distance traveled could be found by summing the areas of the rectangular strips. So that is the next portion. So we're going to make rectangles. The question is, which way are we going to, how are we going to line them? If we split them into rectangles, is the left side going to be touching the function? Will the right side touch the function, or will the middle, like middle of the rectangle, is that where it would be? So, rectangular approximation method. The width of each rectangle is determined by the length of each subintervals. Okay, take 2 hours and break it up into 5-minute chunks. So the width there would be 5 minutes. Versus if I break my 2 hours into 1 second chunks, okay, the width is 1 second. And the height is the function's value at each endpoint. So, LRAM, left-hand endpoints. It's the left-hand rectangular approximation method. That's what LRAM is. Left-hand rectangular approximation method, because we're approximating the area. It's not going to be exact because we don't just have a nice straight line. You know, we have like some curves, and so if I'm trying to approximate with rectangles, it won't be perfect. And that was my intention of showing you this guy. All right, you see how it's overestimating? Right, so when it first starts, you can see the area, and this is how many rectangles we break it into. This is why I chose this one, because it will help you see. All this area is not actually under. And then as we get more and more rectangles, our area is getting closer and closer to what number?
14.
14, right?
Yeah,
14? 13. Ooh, yeah, somewhere around there. Let's see. So we're overestimating. We're still a little over. Getting very, very close. It's about 14. Because imagine the smaller interval. If we could have an infinitely small interval, that's like the next step. That's the third lesson. But I just hope you're understanding what we're trying to do. Okay. Let's try this first one. So we're going to estimate the area under a curve f of x equals x squared from 0 to 3 with 6 subintervals with LRAM, RRAM, and MRAM. Cool. Left hand, rectangular approximation. Right hand, rectangular approximation. Midpoint, rectangular approximation method. Oh my gosh, that's why we say RRAM. Much shorter. So notice LRAM, the left point of each of my rectangles, will touch the function. Am I getting the exact area, overestimating, underestimating?
Exact.
I am underestimating. Because I'm not including this section, I'm not including this area, I'm missing this area, I'm missing this area, and I'm missing this area, right? I'm missing all of that I just colored in.
How do you get it perfect?
That is the question. Perfect. All right, I see you. So that's like the third lesson we're gonna learn. Okay, not doing it today. Okay, so I'm going from 0 to 3, right? This whole length is 3. So what is my interval here? So how many rectangles do I have? 1, 2, 3, 4, 5, 6. I have 6 rectangles.
Yeah.
Because there's one right here. It's equally partitioned. So 1, 2, 3, 4, 5, 6. Okay, so if I take, let's see, my base, let's see, is 3 divided 6 times. Each of these are going to be a half. So this is a half. Oh, come on. Why are you so slow? This is a half. Here's 1. 3 over 2. 2. 4, 5 over 2. And then we have 3. Okay, so if I want the total area, it's going to be, I'm going to add up each area, right? Base times height. The first base is 1/2. The height is 0, because that's why you don't see the box, because it's literally a height of 0. The next one, right? The next box, base times height. So I'm dealing with this box now. I have a base of 1/2. What is my height?